Okay, welcome everybody. Thank you for coming back. It's good to see you all again for our final workshop in this series of Intro to R workshops. So I'll put the link in the chat window one more time. Could somebody just give me a thumbs up if you can hear me okay and you can see my screen okay? Thank you, Katie. All right, let's get going. As usual, the first few minutes will be review. So if other folks join in, feel free, we can catch up. So since last week, I did a couple updates about the website, the workshop materials. So you probably saw over the weekend, I did send out a homework assignment from part 3. So feel free to check that out if you want to refresh what we covered last week. And there is an answer key there as well. So a couple of people did send in their homeworks, and there's a couple ways to do these things. So I would say after you've done it, look at look at the answer key regardless, just to see. Sometimes there's always multiple ways to do a lot of things, and the answer key could show you one that maybe you hadn't thought about. Also, the recording from last week is now also embedded on the website and on YouTube. So feel free to check that out. If you missed last week, I have not yet published the recording from 2 weeks ago, but I'll get to that one soon. Before we jump in, any questions from last week? Anything that we covered last time? Any questions about what we're doing here? Okay, I will. Question. Okay, so we have somebody taking notes with a otter.ai. That's great. Automatic notes. Okay, let's go into the set of slides then. We are a small group today, so feel free to unmute yourself if you have questions regarding anything that's come up. But we'll start with doing a little bit of a review. Okay. So you might remember last week, it was all about data wrangling, and I gave sort of my take on what data wrangling is. And it's basically anything that you need to do to get your data ready to go for what you're trying to do with your data, which might be analysis, might be exporting it back to disk, or sharing some other format, or doing a visualization. So sometimes you have to work backwards. That's a general technique. To kind of like figure out what what you're trying to get to. But data wrangling is a term that encompasses a bunch of different operations that we often do with tabular data. And you can see the list here. You're manipulating your rows, manipulating your columns, reshaping the data, and so on and so forth. Okay, and we looked at all of this stuff last week. Okay, we also talked about tidy data. That's often what you're working towards for many R packages. Not all of them, I would say, but many R packages, they like to see data, tabular data, where every column represents a variable, every row represents something that's been observed, something that's been measured, and then each type of observation is saved in its own table, right? So that's frequently what we're trying to work towards. And you have to sometimes you have to work backwards to figure out how to get from what you've got now to what you need to produce for your stats test, for example. We also talked last week that some of the pain in importing data and getting it ready can be dealt with when you actually import it. And we saw some packages last week, which are designed entirely for importing and exporting data from different file formats. And all of these packages have arguments that you can use when you're importing them to skip rows, to skip comments, to change the column names, to specify the column types, and so on and so forth. You don't have to import messy data and then deal with it within R. But if you do have data that you've imported and you do need to do some manipulations, dplyr is a phenomenal package for this. Here's some of the functions that we looked at last week to subset rows or columns, and then to manipulate rows, to sort them or to create new columns. Okay, so we covered that last time. Something else, commonly, you have two tables and you have to bring them together somehow. So if the tables are related based on a common column or columns, you can use one of these join functions. If your tables just simply need to be stacked together, they have the same columns, the same order, the same names, and the same data types, then you can stack them together using bind rows. Again, these are all functions from dplyr. And we saw a little example of that. If you do have data that's got lots and lots of rows and you need to put it in columns or vice versa, that's called reshaping. And then tidyr is the go-to package for that. All right, we saw some examples of that. We'll see another example of that today. And then finally, getting more towards kind of analysis kinds of questions. It's often common that you want to group your rows, and then for every group of rows, you take some summaries, right? So you might group the row by, the name of the county or the census tract or the plot or the crop, whatever. That's often really changing the unit of analysis. So it's not just a mechanical grouping, but a lot of times, think about it, you're changing your unit of analysis when you're grouping. And then typically, after you group a data frame into rows using group by, then you immediately follow that up with summarize, and summarize is the function that you can use to generate columns of summaries for each group. So new columns containing summaries of those groups, and then the expression that you put in summarize would be any of these functions that are aggregate functions. They take a bunch of different values and then spit them out, a single value. Okay? All right. A couple kind of tips that came up from homework questions. We have seen previously that RStudio has the ability to preview a data frame in a view pane that you can scroll around a little bit like a spreadsheet. And a couple buttons, I don't know if I pointed out, but I'll point them out here. One of the reasons this is a handy thing to do is there is a filter button in the RStudio viewer pane. And when you click that, then these boxes show up here. So if it's a really big data set, like too big to scroll through, you can use these filter buttons and then you just start typing in here. So for example, if I started typing in here garbage, then it would kind of like dynamically filter the rows to only those rows where, the word garbage appears in that column, right? So that filter function is really handy. Again, particularly when you have large data frames. And then there's also little buttons here that you can use to sort the data frame rows according to a column. Okay. So yeah, so that's one of the more useful bells and whistles that RStudio gives us. Okay, so that's what we talked about last time. So what we're going to look at today, we're going to start with some more data wrangling topics, specifically looking at time series data, which is pretty common in research, certainly in environmental research. You often have time series data. So, and it's often can be painful to handle these kinds of data. So we're going to talk about working with dates and times. We'll come back to talk about how to handle missing values, which, if you've got time series data, missing values are a problem, right? They kind of break your time series. So we'll talk about that, and then we'll do a notebook exercise, and then we'll do plotting after the break. So let's talk about date and time data, right? Just like, how do we handle this? So some of the challenges that you may have to deal with working with date or time columns is a lot of times they're saved as text. You get it as text, whether that's a CSV file or you're scraped a website or something. And as we know, it can be formatted in different ways. You might get any combination of this or other stuff. And these are just the dates. Now you just imagine time values are even more variable. So that's challenge number one, is that we often have to deal with text. Challenge number two is that formatting is often based on the region of the person or organization that published it. So if you're getting a data set from Europe or a place like that where month and years are reversed, you're not quite sure what you're getting, and it's often not documented. So these are some of the challenges of working with date and text data, right? You've got all these variations of how they're imported. So let's talk about date and time classes in R, because the good news is that R is really good at handling dates and times. So there is a class, and we've seen numbers, we've seen characters, but there's a date class, and it's designed to hold date data. And if you just type at the console sys.date, it'll return today's current date as a date object, right? So when it prints out to the console, it looks like it's text, but it's actually a date object. There's also an as.date function that you can use to parse or to convert a text string, such as this one, into a date object. Okay, we will see more examples of that soon, how to parse text into dates. So that's the date class. There is a couple classes that can store time values, and POSIX-CT is the main one. I forget what POSIX stands for. It's an acronym for some international open source standard for recording dates, I think. But anyway, so sys.time will return the current time as a POSIX-CT class object. And again, when you view it at the console, when it prints out the results, it looks like it's a string or a character, but it's not. And in fact, here you can see we're wrapping that in class, and we're actually seeing it is POSIX-CT. POSIX-T, you can ignore that for now. That's the parent class of POSIX-CT that inherits some of the properties. So those are the classes of objects in R. And once you get your date and time values into proper R objects, then your life gets easier, because R has functions that support dates and times pretty robustly. If you have a date object, you can format it back to text however you'd like. There are other functions if you want to pull out the month or the hour, or if it's AM or PM, all that stuff. You can extract the date and time, the parts. Julian numbers, that's just the day of the year. That's another kind of date part. If you are working with time data, the time zone is actually saved automatically. That's not an option. It will save a time zone. If you don't specify what the time zone is, it's probably going to be your local time zone, or it might be a UTC, Greenwich time. So that's a detail that sometimes can get a little painful, but time zones are saved, and you can convert from one time zone to another. You can do all the kinds of mathematical operations that you might think, like, is this date greater than that date? That works. You can add dates and intervals together, all that date time arithmetic, subtraction. You can compute intervals. That sometimes that's really important, like looking at defining intervals, and then it's functions that kind of analyze intervals. If you are plotting, if you're doing a time series plot, and say you have time on the x-axis, it'll format them nicely. You don't have to do a lot of painful manipulations to have it appear, as a nice axis labels, and so on and so forth. So once you get your data into one of these classes, then your life gets easier. Working with time data. Lubridate is a package from the Tidyverse, and it's designed to help you manipulate and work with time and date data. So you don't need to use it. You can do all of this in base R, but Lubridate is a nice one. And here are some functions that Lubridate provides. So if you do have text data, maybe it's a column in a data frame that you got from somewhere, and you need to convert it to a date time object, there's all these ones here, and you just kind of pick the one out, like, this is things. If the text data is in this, let's look at this guy here, right? So here we have a character object, and it looks like we have the month, the year, followed by the month, followed by the date, followed by the T, which stands for time, and then hour, minutes, second. So if this was what we had to work with, we could use this function from Lubridate, which is kind of designed to parse or to split up that value. And it'll figure out whether there's slashes or dashes or spaces. It'll kind of intelligently look at it and give you a pretty good guess. And so these functions usually work, I would say they work 90% of the time. They figure out how to do it. All of these functions up here, if you need to specify the time zone, and you probably should, it's probably a good idea not to leave it up to chance. There's an optional argument that you can provide to pass the time zone value, right? So if you're Pacific time, it would be this. There is a little bit of a gotcha though, in that you can't say time zone equals, PSD, Pacific Standard Time. You can't use those abbreviations for this time zone argument. What you have to do is you have to look up the proper name for each time zone, but there's a function here that if you just type Olsen names at the command line, it'll tell you like I don't know, there's like thousands of time zone names that you can use. So you just pick one of those. Another pro tip is don't name your variables date, because that's the name of a function that's pretty generic. So pick other variable names to save your date data. It's not a problem to name a column date. That doesn't usually cause a problem, but okay, so this didn't render yet, but there is a function that we will see in the exercise coming up, where if you do have the month in a column, the year in a column, the day in a column, there's make date and make date time, the functions from the tidyverse that will put those together and give you back a date column or date object. Okay, finally, so if you are saving data to disk, which is often something we do, if you are saving it to a text file format, well, first of all, the number one choice would be save it to a file format that actually records that this is a date field. So any of the file formats from stats programs like Stata, SPSS, SQLite, all of these file formats allow you, in fact, require you to specify a type for that column, right? So if you're using one of those, you don't have to worry so much. You just have to make sure you're saving an actual date object. But if you're saving your data, again, your tabular data, to a file format like CSV or Excel that does not enforce date types for each column, then my recommendation would be to save it as character data or text data and format that in an unambiguous format. And fortunately, there's a few of those that you can use. If you're working with date data, putting the year and the month and the date, separated by dashes, that works. If you're working with date time data, including a time zone, for example, you can use ISO 8601. And the Lubridate package actually has a function that will format dates and time values in that. So it's called format ISO 8601. So again, if you are saving your data frame to disk that you can come back to and keep working with, either save it in a file format that records the type of each column, including just the native R format. We haven't seen that yet, but you can actually save data frames as R objects to disk and bring them back into R. Or if you are going to save it as a text file, save your dates as text and just use one of these format functions so that it's unambiguous when you bring it back in. Whoever brings it back in will know exactly what kind of how to parse that column. Okay, that's a bit of a detail, but feel free to ask questions if you have any questions about that. Okay, finally, before we do the notebook exercise, let's talk about missing data. We've mentioned this a few times before. So, and this is often something you have to handle when you're working with importing data. So we've already seen there are a couple functions that you can use that will tell you, is this data, is something missing here? And again, missing values are recorded by NA. It's kind of like a constant in R. as opposed to like -99. Sometimes you see that as well. Sometimes that's something you have to handle. Let's convert those -99s to NA values. So is.NA will tell you if it is missing. You might remember when you put the exclamation point in front of it, that negates it. So that'll return the opposite, that it is not missing, depending how you're using that. So one way that you can deal with missing values is simply to ignore them. And a lot of the functions that do compute summaries do have an optional argument that you can pass to tell it to ignore or to remove the missing values and to compute the mean or the median or the whatever it might be with all the other values that are not missing, right? So that's one way that you can handle missing values. You can also fill them in with a constant, right? So you just compute the average of all the other values and use those as kind of a proxy or an estimate for those missing values. We'll see an example of doing that. And then you can also impute the missing values, which is a little bit similar. You're putting in approximate values for those ones you're missing, but you're doing a little bit more smart than just taking the average of all the other ones. You could repeat the last value. If it's time series data, that makes sense. You can do linear interpolation and you can do spline interpolation and many, many other methods that I'm not so familiar with. But imputing missing values, that's a whole field of statistics. And there's lots of them. We'll see some packages that have functions that give you a lot of options there. Okay, so with that, we will go into our first exercise, and we'll be pretty well on time here. And what we're going to do in this notebook exercise is we're going to work with some weather data, which is a little bit notorious for having missing values. So specifically, we will get some data from one of the CIMIS weather stations. In defense of CIMIS, so I will say that these data there were no missing values from this station, but I made some missing for the purposes of our exercise. But we will import some weather data from one of these weather stations, and that's what they look like. If you're not an ag person, CIMIS is a network of weather stations that's managed and funded by the Department of Water Resources within California. And they're really designed to help collect data to help inform irrigation scheduling, basically. So they tend to be over grassy areas, not on crops, but on grassy areas. And then they measure evapotranspiration and that kind of stuff. We'll talk a little bit more about how these are useful. But in the exercise, we'll combine different date part columns into a single date column. We will do some reshaping. We'll look at how do you know if you've got some missing values. See a couple of ways you can do that. We will replace some missing values with a couple of methods, and then we'll do a little data sampling. Okay, so that's next. I will put the link in the chat window for our workshop, RStudio project on Posit Cloud. So go into Posit Cloud and log in if necessary, and then click on that link in the chat window. And this is the same VM that we've clicked on in the past, but it's been updated for today. So please click on it, and you'll know that you've got the right one because it says Intro to R Part 1, 2, 3, and 4. So that's the name has been updated to reflect that it's got all sessions here. And then click Save a Permanent Copy as soon as it opens up. And so again, go into Posit Cloud, click on that link in the chat window, and then once it opens, click Save a Permanent Copy. And I'll wait a couple minutes for people to give me a thumbs up when you've been successful in opening this project. I'll wait a second because in case anyone needs to log in Posit Cloud. All right, so assuming that you have Posit Cloud open and you have our RStudio project open, go ahead and click on the exercises folder in the file pane. and you will see one called, you'll see a notebook called NB Data Wrangling 3. NB Data Wrangling 3. Go ahead and click on that. It will open up in the view pane, sorry, the source pane. Yes, I'll put the link again. So go ahead and click on the after you open up the project and click Save a Permanent Copy. Go into the Exercises folder, click on the Data Wrangling 03 RMD file. It's our notebook. And I'm going to go ahead and minimize my console because this is a notebook. And you might remember with notebooks, the output of code chunks appears inline, so we don't really need the console. All right. Okay, so let's just jump right into this. So go ahead into code chunk number 1 and run the whole thing. You can click the little green arrow button or Control-Shift-Enter on your keyboard. And this should look familiar. We're loading dplyr as we always do, and then we're specifying our package preferences for the filter function, the count function, select function, and arrange function. So from here on out, we don't have to worry about name clashes across different projects, different packages having the same function. Okay, then let's go ahead and run code chunk number 2, and then we'll talk through it. I run the whole thing. This is new. It's something we haven't done before, but we are importing some data. We're importing some weather data, as I mentioned, and it's on Google Sheets. And if you want to take a look at it on Google Sheets, you can see the URL there on line 28. You can just kind of copy that URL to the clipboard. If you're curious, I think you can if you hit Shift and click on it, that doesn't work. That used to work. But you can copy the URL to the clipboard and open it up in another window. And you should see, you probably don't have edit access, but you can see the data, right? I'm a big fan of Google Sheets for, we talked a little bit last week about collaborating on data analysis. Google Sheets is a tool that might be helpful for that. All right, so this is the data. This is just came down this morning. These are a few weather variables from the CIMIS station in Arvin, Edison, which is south of Bakersfield. I tried to find a picture of the actual station, but I couldn't find it. But I'm going to keep looking. But let's go back to so these are the columns it comes that you get via the API. And let me go back to our notebook here. And let's talk through code chunk number 2. So we're loading up Google Sheets 4. That's a package that you can use to both read and write from Google Sheets. And the GS4DAuth, that is simply telling R that what you're trying to do is made public. If you don't put that, it's going to prompt you to authenticate with your Google account. And if you're trying to pull down a Google Sheet that's private to you, then yes, you have to do that. But what we're dealing with here is available to anyone with the link, so we don't have to worry about that. On line 33, we are using the read_sheet function from Google Sheets 4. We're passing it the Google Sheets URL and the name of the sheet, which is not really necessary because this particular Google Sheet only has a single sheet. It would have figured that out. And we get a tibble, right? We get a data frame. If you want to see the whole thing, you can run line 35. You can remove the comments or just highlight that line minus the comments and hit Control-Enter. But you can see the columns, right? That we're working with. And note that the date column has been split across year, month, and day. Right, so our first task is going to be to combine those into an actual date. Okay, so moving down, there's a big blank space. I'm not sure why. If you're curious and interested, if you're interested in working with the CIMIS data. There's a gentleman, Michael Kuhafkan, who wrote an R package. The CIMIS system does have an API. It works great when it works great. Sometimes it's oversubscribed and it doesn't work, but I find off hours it works really well. And you can use the package that Michael wrote. I think he was a grad student at the time at Davis. And it's got some functions that makes it pretty easy to bring down CIMIS data. So question number one, let's pause at question number one, or challenge number one. Would you consider the CIMIS data A, to be long and wide, and B, is it tidy? So I'm going to open up that CIMIS table that we just got. I'm going to open up in the view pane. So I'm going to highlight the view command that we saw before and just run that by itself. So question for the audience. Is this wide or long? Let's scroll down here. And anybody want to hazard a guess? The tip here is that this data set contains 30 days of daily weather data from this particular station, and it's got 3 or 4 variables. It has your daily minimum, daily maximum temperature, evapotranspiration, precipitation, and ASCE evapotranspiration. I don't even know what that is. Okay, Gary thinks it's long. Anybody else have a thought about whether this is a long or wide data frame? It does have a bunch of columns, but I would agree with Jerry that this is long because it's, you know, it's 30 days of data and we've got 150 rows, right? And the reason it's long is because this one table combines the different variables, right? So you see that item column, and that tells you what is the variable, the weather variable for that row, right? So it's stacked them all up together. So this is a long table. All right. So, and then what about tidy? Would you call this tidy? This is a little more subjective, perhaps. Does every column contain a variable? Yes, right. I think that's pretty good. So it's well structured. Every variable is saved in its own column. What's the second one? Does every row represent an observation? Yes, I think it checks that box also. Each row represents an observation of a weather variable. The fourth property of tidy data is every type of observation in its own table. And that one, maybe yes, maybe no. I would probably say no, because temperature, minimum and maximum temperature, yeah, that's the same kind of observation, but ETO is pretty different. Like the units are different, right? So I would say this is not tidy data because it combines multiple types of observations. And ideally, you know, you want your table to have a single kind of observation. Unless for some reason you're plotting, you know, evapotranspiration on one axis and temperature, average temperature on another axis, something like that. And it's really easy, of course, to filter these to get a certain one, which we will do next. Okay, so that's so that's challenge number one. So back to our notebook, come down to code chunk number 3, starts around line 59. And again, if you haven't been running the code chunks above, you need to do that in a notebook. You can always click the run all chunks above if you're coming in late and catching up, for example. So in code chunk number 3, I'm going to go ahead and run it, and then we'll talk through it. Our goal here is to create a column that contains an actual date object, right? And in this particular data frame, year, month, and day were separated as separate columns. So fortunately, the lubridate package has a function called make_date that allows you to provide the day, the month, and the year as separate arguments. So we use that with the mutate function from dplyr, which creates new columns. And we're calling the new column DT. just to help my brain remember that this is something that we built ourselves. The relocate function, we haven't seen that before. That's another dplyr function, and you can use it to change the order of one or more of your columns. So, and you can preview, and you can see that, yes, the DT column does indeed have a date object, because you can see the character or the column type in the preview of the data, and it did actually combine the year, the month, and the date columns properly. And we don't even need those anymore. Right? We'll just work from the date column. Okay, any questions? Okay, so that was a task of not parsing text data into a datetime object, but combining date part columns into a datetime object. In this case, it's just a date object. Okay, next, code chunk number 4. Let's go ahead and run this. And what we're doing here, as we saw previously, this is a table in a long format. And we are now, there's actually 4 variables put together. So in code chunk number 4, after you run it, now each variable, each weather variable, it's in a separate column, right? So this is certainly easier to digest because every column's in its separate format. Every column represents a different variable. And how are we doing this? We're using pivot wider. You might remember we did see that last week. Pivot wider is a function from tidyr, and that's what you use to go from long to wide formats. And I won't talk through all the arguments, but basically names from, that's in the original data frame, like what column to use as the names for the new columns, and to divvy the values up across those new columns. We need a values from argument. And then ID calls is simply the columns that we want to appear at the front of the table to identify each row properly. So you might notice all of those extra columns have been dropped. And that's because we manually specified the columns that we want to keep to identify each row. In this case, all we really need is the station name and the date. Okay, so that's another example of using pivot wider. It's a really handy function. And I did put here the URL to a vignette from the tidyr package that gives lots of examples of pivoting, both wider and longer. Okay, no questions, so let's keep going. And code chunk number 5, we're going to start looking at missing values. And step number 1 is to diagnose. Do we have missing values? How many? Where are they? So code chunk number 5, go ahead and run that. All we're doing is creating a new table which only has the ETO, column or variable. That's evapotranspiration, so it's a measure of how much water has come out of the crop, both through plant respiration as well as evaporation. And this is the key metric that allows irrigators to know how much water they need to put back on the crop. I know a week has gone by since they last irrigated. They can figure out how much water has been lost. That's what you put back, and your crop stays healthy and you don't waste too much water. So you should be able to follow code chunk number 5, I hope. It's pretty straightforward. We're using the filter function to only grab those rows where the item value is evapotranspiration. And then we're using the select function after that to only keep 5 of the columns. So again, throwing away all those other columns, and that's the result. However, we might have some missing values. So if we're going to do any kind of analysis or plotting, we need to deal with the missing values first. So how do you know if there's missing values? Well, one way you can do it is you can just scan through the data. So the view function, it's I'm just going to highlight it here. Just not highlight the comment characters, but just highlight the view command and hit Control Enter to execute just what was highlighted. And now I can scroll down, and yes, I see in the value column, there are some missing values, right? So, which is not uncommon with weather station data. Things go offline, For some reason, a measurement was not made. Okay, so we do see some missing values. So if your data frame is not too big, and this one's only 30 rows, so it's not too bad, but imagine it was 30,000 rows, right? You couldn't really scroll through 30,000 rows unless you're very patient. We saw last time that the summary function, which is from base R, will provide, when you run that, then that will present for a data frame, for every column, it'll show you a little summary. And if you look at the value column, it'll also report if there were missing values in that column, and if so, how many. All right, so that can tell us there are 5 missing values in that value column. Right, the other columns all look fine. Okay, so how could we handle these missing values? Well, this is where you have to make a decision. One option would be to ignore them. One option would be to fill them with a constant value, such as the mean or the median of all of the other values that are not missing. So that's what we'll do first. So in code chunk number 7, we have to decide, should we use the mean or the median? Like, what would be the most reasonable replacement value for this data set? So generating a histogram is a good way to think about this, because if data is heavily skewed, meaning it's all bunched up at the one end or the other, then you might want to use the median, because the mean can be affected dramatically when your data are not sort of uniform or normally distributed. So this data set does look like it's a bit skewed. So if I was looking at this and I was the data analyst, not knowing much else about the pros and cons of medians versus means, I would go with the median. So in code chunk number 8, we've made that decision. I think it was a little subjective, but we made the decision. Let's fill in those missing values with the median of all the other values. So in code chunk number 8, we're actually computing the median. And note the median function, like other functions, will return NA if any of the values are missing. So you have to pass that NA.rm optional argument to actually get a value back. So now we have the median value saved as an object. And in code chunk number 9, go run code chunk number 9. And this is where we're actually replacing the missing values with that median value that we just computed. And let's look at code chunk number 9, because there's something new here that we haven't looked at before. So code chunk number 9, we're generating a new table. We're saving the results into a new table called fix1. But look at the mutate expression, right? So we're mutate, as we've used it a lot, we're defining a new column. But here, for the values of the new column, we're using if_else. So if_else is the function that you can use. It's one of the functions you can use if you want the values of this new column to be based on an if-else kind of logic, right? So the if-else takes 3 arguments. The first one is, in this case, it's is.na, and then value, which refers to the column value. So if that evaluates the true, then if-else will return the next argument, which in this case is that number that we just computed, right? If is.na is false, meaning there's nothing missing there, then if-else will return the second or the third argument here, which again is value, and again that refers to the value of the value column. Okay, so that's how we are only replacing the rows where there is a missing value. Right? So that's how you do that using mutate. And if you want to verify that actually worked, if you again run the view function to open up this new table we created in a new viewer pane, and we come down here, I can see that new column, and I can see, yes, indeed, where there were missing values, they did get filled in with that median that we computed. All right, any questions? Okay, let's keep going then. So that's one way that you can replace missing values. Another way that you can do is a little more intelligent, particularly if you have time series data. You can interpolate the missing values, and there's a few options there. You can repeat the last value. You can do a linear interpolation. You can do spline interpolation, which is where it uses a little curvy estimate between the two values. There's a few packages that do this. Zoo is one of them, and the Zoo package has a function called na.approx. The Zoo package in general, it's designed to give you a bunch of functions to work with time series data. This is just like one of several dozen functions that it provides for that. But na.approx, that will, you pass it a vector of values, and there's an assumption there that they're evenly spaced over time. And where it does find missing values, it will do na.approx does a linear interpolation. So it sees, well, what was the last non-missing value and what was the next non-missing value, and it fills in the other ones with a linear estimation. So you can go ahead and run code chunk number 10, where we're computing the values again just for that column, and you can see there are no missing values there, and there is a string of a 0.18 which is where the missing values were added. We'll look at that in the view window soon. There is another function from the Zoo package that you could use to use a spline model, again, to kind of bridge the two missing values. That's probably not appropriate with weather data, with daily weather data, but for other kinds of time series data, a spline might be more appropriate. Yes, and of course, if this, if we were meteorologists, we would have probably more appropriate methods for this type of data, but we're just using some examples here. So in code chunk number 10, we created replacement values for that column. And in code chunk number 11, we're going to take that column of values and we're going to add it to our table. And note here, something else is kind of different in code chunk number 11. Run code chunk number 11 if you haven't already. Notice here we're using bind_calls. That's another function from dplyr, which basically adds a column to your data frame. And the assumption there is that that vector that you're adding has this appropriate number of values, like one for every row, and that they're in the correct order, which those are safe assumptions because we just made those values from the existing columns. So if you look at code chunk number 11, you can see fix.2. And if you were to open that up in a view window, view pane, I'll go ahead and do that. We're going to highlight again just the view command right above it. And now if I look at, now I see two columns that we've constructed, fix1 and fix2. And if you find the rows that were missing, we can see that fix1 all replaces the missing values with a constant, 0.18, and fix2 replaces the missing values with interpolated values, again, from the last and the next non-missing value. That may or may not be appropriate for this kind of data, but it shows you examples of how you can do that in R. Impute.ts is another package which has lots of functions for imputing missing data, other kinds of methods. Okay, excellent. Any questions? All right, please do speak up.
Oh. Why do you say this may be not appropriate for this data? Like, basically it's saying, okay, this day maybe was a little cloudy, and then I'm missing 2 days, and then the following day is sunny. And so let's say that the first day that I'm missing was kind of a little cloudy and sunny, somewhere in between, and the following day was a little sunnier. Let's linearly interpolate between those 2 days, and let's kind of guess how much it would have been, it could have been, right?
Exactly, yeah. So you're articulating the domain questions, the science questions, if this was my data set, I would want to call like a biometeorologist who works in the valley and say, hey, how would you guess missing evapotranspiration data in a time series? And it might be, so over the map that maybe you can't, but maybe, maybe there's other data that you could get, like, cloudy, what was it, cloudy or not, and use that in some sort of smarter way to fill in those missing values. So, or maybe in practice, it's really hard to do, and just, put in an average and, hope for the best. So anyway, there's domain specific questions. If this was economics data or population data, there are all these, there's people who study how to replace missing values depending on the type of data in general. But whatever method you want to use, you can probably do it in R. Challenge number 2. I'm going to skip this, but if you want to tackle this, there is another variable, the daily maximum temperature, and there's some missing values there as well. So your task in challenge number 2 is to think about how would you replace missing values of the maximum temperature. Just make your best guess, and then use that method and implement it to fill in the missing values. All right, but in the last couple of minutes before we take a break, let's do one more little operation here. And this is where we're going to resample the evapotranspiration values into categories, low, medium, and high. And sometimes this is something you need to do as well. And that's what we're doing in code chunk number 12. So go ahead and run code chunk number 12, and then we'll talk through it. Just go ahead and run code chunk number 12. And you can see in the output of code chunk number 12, a new column at the end there called ETO level. And that's a character column. It's got the labels high, medium, or low. If you opened it up in the view pane, you would see some more. So how did we create that column where we're taking the numeric values and we're putting them in these categories? There's a few ways you could do it, but if you're doing a relatively simple binning of the data, in this case into just 3 categories or 3 bins, you can use the case when function. So if you look at code chunk number 12, we're using mutate, as you would expect. That's what you use when you want to add a column. And then the expression for the values of this new column is using case underscore when. We already saw if underscore else. That's one type of function that you can use to assign new values based on a logical rule or condition check. Case when is another one. Case when, it's similar, but it allows you to specify as many cases as you want. So here we're chopping up the data into 3 categories, and we're manually specifying the breakpoints there. You can see in the expressions. But you can also see that the syntax for case underscore when, it's a little bit funny, right? So you have your logical expression, is the value fixed less than 14? And then there's the little tilde, and then the label low. So that's not common. That kind of syntax is not common. But if you look up the help page, or if you look at the cheat sheet, you'll see that's how you use the case when function. And it does the job, right? So basically, it'll evaluate each of the expressions in case.when. It'll evaluate the expression on the left side of the tilde. If that's true, it puts in the value on the right side. And then the very last one that says true, that true just means and everything else, right? So if it's not low and it's not medium, and that everything else, that last expression will evaluate to true because the expression is true. So everything else will get the label high. And it goes through them one by one. So whichever one, when it hits one, it stops, right? So that's kind of how that works. And there might be other ways to do this as well, particularly if you're binning and you've got regularly spaced bins. But this is how you can do it with dplyr using case when. Okie dokie. All right. Any questions? Any questions? All right, let's take a break then. I see. Yeah, so that kind of concludes data wrangling, and we've gotten a lot of tools that you can use to work with tabular data and to get it ready. And I've mentioned before, often your goal is a data frame which is tidy, which meets those properties, but it's variable. Like right now, I've been using a package called chillr to compute chill portions. And it's an older package, and it doesn't want tidy data. It has a very specific format that it expects your temperature data to be entered in, including, like, I think the column names. So I had to read the help files. I had to look at the help, the examples to figure out, like, what is the endpoint of my data wrangling. So, but you've got a full toolbox that you can use to do probably everything. But one of those is going to be plotting. So let's talk next about ggplot, which is a package that's designed specifically for plotting. Ours is a pretty good plotting platform, and ggplot is a big part of that. The name of the package is actually ggplot2, so this should be ggplot2. But let's look at an example of a ggplot expression, and then we'll kind of unpack it. So here's our penguins data frame. We've seen this before, right? So a handful of columns about penguin measurements. Each row represents an individual penguin. And it's in a wide format, right? So every column represents different biometric variables, and it's got some missing values. So let's say we wanted to make a scatter plot. This is an example of a ggplot expression that created this plot. So as you can see, to create a ggplot, it's more than just the plot function. We've seen the plot function, we've seen the hist function, we've seen box plot. Those are all plotting functions from base R, and they work. They do predictable things, and they've got lots of vector arguments. ggplot's different. ggplot, you can already see just at a glance that it's actually several functions that are being added together, and each of these functions adds something to the plot, right? So take home number one, when you're using ggplot, you're probably not writing a single function, and you're not piping them together. We're using those plus characters, right? But just with the default values, you can see the default values are this kind of like shading in the background, and it looks pretty good just out of the box. Certainly a little bit nicer than those base plots. So let's take a look at this expression a little bit more closely. So ggplot. So as I just mentioned, a ggplot expression is built by adding a series of functions together. And again, we're using the plus sign, not the pipe operator. So that's difference number one. But it is a series of functions that we're combining, chaining together. The first function is always going to be ggplot. Again, the name of the package is ggplot2, but the name of the function is just ggplot. And this function kind of like sets up the canvas. And if you look at the arguments in here, we'll look at these arguments a little bit more closely, but that's what this ggplot function does. It creates a canvas, it sets some default values, and then the subsequent functions actually do the drawing. So the ggplot function, the first argument should be a data frame. ggplot wants data frames. If you've got your x variables in one vector and your y variables in another vector, you got to stick them together in a data frame, right? So ggplot wants a data frame, which could be a spatial data frame if you're making maps, but that's a little bit of a tangent. All right, and that data frame becomes the default data for everything else in your ggplot expression. All right, it's the default. You're not locked in, but it's the default. The second argument for ggplot is where you're basically specifying how those different columns in the data frame should be used when it comes time to start drawing things onto the canvas. Okay, and you pass it a function called AES, which stands for aesthetics. Some of this terminology, it's a little untraditional, shall we say, but it's basically the AES function is how you specify how each of the columns in your data frame should be used as a default. So X, right? So there's, we're making a plot. There's an X-axis. So whatever we're drawing could be lines, could be symbols. We need X values, right? It could be a box plot, could be a histogram. Likewise, Y, and we're basically telling it here to use the values from the flipper length millimeter column. That's one of the columns in the data frame when it needs to draw things on the X-axis. Likewise, the default column to use when you're putting things on the Y-axis is the build length column. And then here, we're saying the default color, when you're drawing dots in this case, should be mapped to the values of the species column. So in other words, we're setting up the default mappings between how things get drawn on the canvas and the columns in the table. That's the second argument of the opening ggplot. After that, you're going to have one or more functions that actually draw things on the canvas. GeoPoint is a function that draws points. All of these functions start with the word geom, and there's a bunch of them. That you can do geoms for bar plots and line graphs and all kinds of stuff. There's a whole bunch of them. And there's a bunch of packages which add even more. And basically, you simply add those in. What we're looking at right now is a scatter plot. So there's like only one layer, it's just points. But we could have on top of that scatter plot some other stuff, like a trend line, or dots on tops of bubbles, or bubbles on tops of dots, and that kind of stuff. So you can have plots that have multiple symbols on them. But that comes next. So you have one or more of those. And again, they're going to use the default values that you've set up at the beginning, the default data frame, and then the default columns to draw those points. And then finally, you could have one or more functions that you tack on, usually at the end, that provide other options to customize how the plot looks. The title, what the title should be. You can have a caption. You can have, should there be a legend? Should it be here or there? Should your plot have a fill color? Yes or no? And so on and so forth. So there's lots of these other functions that you can use. And again, they usually come at the end that kind of specify the plot as a whole, the colors that it should use, and so on and so forth. All right. So in general, that's how you build up a ggplot expression. So yeah, speaking about this a little bit more. So the AES function, that sets the source or the default column for those visual properties. And again, what properties you need to provide default values for, it depends what you're drawing, right? So points, they have a color, but they don't have an outline color or a fill color, right? But if we were drawing polygons or shaded regions, we would need to specify some other visual properties. Okay, here's some common ones: X, Y, color, fill, and size. But again, it's going to depend on what you're drawing in terms of what visual properties you can map to a column up in your data. Okay, that's what this is saying. And there's a bunch of these geom functions. And yes, so the AES function is only needed when you want the color, for example, to actually depend on a column in the data frame. If you're fine for them to all be black or all be red, you don't need to put that in the AES function. Likewise with fill and size. If they're not going to be, if they're not mapped to a values in your data, then you can leave them out and you'll use default values. Okay, feel free to, this stuff's not super intuitive, so, and it's a different way of plotting than most people are used to. So feel free to chime in with questions. Let's talk about the geom functions. They all start with geom, and each one of these will draw a layer like from the bottom up. These are some common ones, but there are some packages that provide other ones that you can use. And there's lots of that stuff, including mapping. They get added to the canvas from the bottom up. So if you want your points on top, then they should be last. If you're going to have maybe some bars, and then on top of the bars, you maybe have like little error bars. That's another kind of geom that you can stick on, the little error bars. Those should go on top. A lot of these geom functions, they have arguments where you could specify the color, you can specify the size. And if you've provided a default column, then that's what it's going to use. It will inherit the mappings that you set up at the beginning, but you can override those. So you can pass the call argument when you call this function that's doing the drawing, and you can feed it a column in your data, which might be different than what you specified as the default, or it could be a constant value, such as the name of a color, or like size equals to 1.5 if you want your dots to be a little bit bigger than the average. Okay, so those visual properties get inherited from the mappings that you set up, and you really have to look at the help page for each of these geom functions to see how you can tweak the appearance. Some of these are pretty obvious, but some of the novel ones are different, like a radar graph, for example. So let's look at an example of box plot geom function, which draws box plots. And here you can see what that would look like. So box plots are two-dimensional. They have X and Y values. So when you set up your ggplot opening function, you do need to specify the X value. And in this case, the species column, that's a character column. So it's going to use the unique values of that column to create separate box plots for each group of those data. And then you also need to tell it what column to use on the y-axis, which is how it draws the box plot. Then, in this example, we're following that up. After we've set that up, we follow that up with the geom box plot function. Because if we don't do that, it's not going to draw anything. You just have a blank canvas. And the geom box plot does accept a color argument, which is the outline of the box. And it does accept a fill argument, which is the fill color. And it specifies a size argument. So we could have mapped the color to a column in the data frame, and likewise with fill and size. But here, we're not doing that. We're just manually providing a constant value. So everything, all of the boxes are going to be have a navy, kind of a dark blue outline, a yellow fill, and the size refers to the thickness of the outline. Right? So that's an example of mixing and matching some visual properties that are linked to the data and some visual properties that are just kind of manually specified as different than the default values. Okay, any questions? Apologies if this is a little bit in the weeds.
You
said, don't expect to do this. Feel free to just kind of watch. Here's an example where. Question?
Yeah, you said we could have mapped that color to some column, but instead we decided not to, and you said we specified the constant value.
Yes.
And so you mean that's why we did not use that AES function inside that box plot function?
Correct. What we could have done, I mean, we could have said X equals species. These two arguments, we could have put them down here in geom box plot.
that would have meant that you plotted, I'm sorry, that you mapped some color to some column. Is that right?
Yes, yes. If we had wanted the colors to be mapped to one of the columns, then instead of the word yellow here, which is a constant, and it knows how to interpret names of colors, we could have put in there the name of a column. I don't know what that would look like with the box plot, but you could experiment. Yeah. Let's do some, we'll do some more. I think you'll start to see what makes sense for the visual properties. So next, we're going to create this plot right here, which is similar, but now you can see there's some more stuff, right? So we have this red horizontal line. Maybe that's the average of the whole data set or something. And we even see a little label up here. So in this example, we're basically, it starts out the same, right? We got this part's identical to what we've just done. But then now we're adding, you can see he's adding other geom functions that are drawing other things on the canvas. Geom H line, that's drawing that red line. This is not linked to the data, right? That red line, you can even see we're specifying the y-intercept as an argument. And we're specifying the thickness and we're specifying the color. But that's an example of how you can add another element. Geom label draws that little label in a box. And again, this is not linked to the data whatsoever. We are manually specifying, put it at this XY location and use this label. And then there's some other defaults for, the background and that kind of stuff. But if you do want to add additional elements, additional layers to your plot, that's easy to do. You just simply add more geom functions and they can be linked to the data or not. All right. So it takes a little while, but you can really you can make some very customized plots with this function, with this package. Okay, without getting excessively in the weeds, we'll see some more examples of tweaking ggplots in our next exercise. Before I go on to that, any questions? Okay, if no questions, let's jump back into Posit Cloud. Wake up your project if it's asleep, which mine is. And once it wakes up, go ahead. I'm going to go ahead and clean up my workspace here. I'm going to close some of these things I have open. Don't need any of these. I'm going to clean out my environment tab, click that little broom icon, deletes all the objects in memory. So a clean slate here. And then go ahead and click on our last notebook called ggplot 101. All right, so after you've cleaned out your workspace, open up the ggplot 101 notebook. And I'll give people a minute here to catch up. Okay, I'll assume that everybody is who's keeping up is doing okay. If you'd like me to pause, feel free to do so. If you have questions. Okay, so let's go into this notebook and we'll go down to code chunk number 1 and go ahead and run code chunk number 1. And I won't even talk through this one because I know we've seen this like zillion times. Code chunk number 2, run code chunk number 2. That's loading up the Palmer Penguins data set. And then let's just jump right down into code chunk number 3. All right, this is where we are actually making our first scatter plot. And code chunk number 3, it's only got 2 functions that we're chaining together with the plus sign. Again, that ggplot function with 2 arguments, the data frame, and then the mappings using that AES function. And then we're following that up with geom point. And if you look at the AES function, we're telling it for the X values, use the flipper length column. For the Y values, use the bill length column. We're not specifying a column for the colors or the size or the shape. We're leaving all those to be the defaults, and we get a decent looking scatter plot, as well as a little warning message saying that there were some missing values. So that's another nice feature of ggplot, that it will tell you that it has taken out some missing values. And the default value is to plot things, but omit the missing values. Okay, so that's very simple plotting. You might notice also in code chunk number 3, splitting the ggplot function across multiple lines. So that's, when you have a function that's got lots of arguments, like it's a little unwieldy, you can split a function across multiple lines. Usually you do that after a comma, after you've passed one argument value. Code chunk number 4, go ahead and run code chunk number 4. This is really similar. We've just added one thing, which is we've provided a value for the color argument for geom point. And the color argument, again, we're not linking it to a column in the data frame. We're just saying, make all these points blue. And that's what's going on in code chunk number 4. So hopefully that looks pretty familiar. Code chunk number 3, though, code chunk number 5, run that on line 72, roughly. And here we are again coloring the dots, but here, if you look at the AES function, we're mapping the color property to the species column. And the default value when you do that is to pick, ggplot figures out, okay, there's 3 unique values in that species column. It picks 3 different colors for default for each group of those values, and it colors them and puts up a legend as well. All that's done by default. We don't have to do anything magical or painful to get that. Okay, so that's linking color to a column in the data. And species, those are character values. If the species column was something else, like if we mapped the color column to like flipper width or something like that, then it would use a color map. It wouldn't use 3 discrete colors. We might do that later. Okay, code chunk number 6. Go ahead and run code chunk number 6. This is really similar to what we just did. We're mapping the colors of the dots to the values of the species column, but we've added one more function at the end of our expression to manually specify the colors that we wanted to use. And these are 3 colors that are colorblind friendly. So that's something to think about when you are plotting or making maps. It's a good idea to use colors that people who are colorblind can actually differentiate. And there's a whole body of there's color palettes that you can use for that. All right, but that's an example of tacking on a function at the end of your expression to do like a manual customization. In this case, the colors that are being used. Okay, so there we go. So let's do challenge number 1 and challenge number 2, 1A and 1B. So 1A, make a scatter plot with bill depth on the x-axis and body mass on the y-axis. And then 1B is the same, but then here it's also suggesting that, we do know there's 3 species of penguins. So make the dots stand out as being different by using the colors of the, by using a color for each species and by making the shape different for each species. So maybe Gen 2 is squares and Adelie is diamonds or whatever, right? So in challenge 1B, your job is to, in addition to using colors, make the points different by species using the shape as well, which we've not seen before. So that's something you have to figure out on your own. Okay, so it's 11:32. I'm going to give you 5 minutes, 4 or 5 minutes. So please tackle challenge number 1A and 1B. And if you get stuck, feel free to unmute yourself and ask a question or ask a question in chat window. And there's also little bit.ly links that you can use. You can click on to go to the answer. Okay, we'll get going on the challenge 1A. So we start ggplot expressions, always start with ggplot. And then obviously the first argument of ggplot is the data frame. So that's penguins. The second argument would be the AES function. And again, that's where we set up the default mappings. It's where we tell, basically we specify which columns in the data frame to use for different visual properties of the things that we're going to draw. And here the instructions tell us make a scatter plot with build depth on the x-axis. So that's going to be x equals to, what is the column for build depth? Is it going to help me with this? Bill, yeah, it's not going to help me. Let's cheat here. Build depth is Bill underscore depth. There we go. Bill underscore depth underscore MM. All right, so we're basically telling it use the build depth column for the X values, and then Y use the body mass column for those values. And that's all we need. That's all we really need. Now, if I just run that by itself, I've got a plot there, but there's nothing on it because it's created an empty plot because I have to, so there's no errors, but it's not finished because I also have to add a function to actually draw something. And in this case, I'm going to use geom_point. All right. So let's verify this looks good. We have build depth on the x-axis and body mass on the y-axis. That looks good. And we can see the default labels. Okay, so perfect. Stick this on the, put this in the chat window. Anyone's interested. All right, so any questions? And then for chunk 8, I'm going to copy paste what I started because that starts the same, but we want the color and the shape to vary according to the species. So I think we can use the col property to vary with by species. So col equals to species. That's where we're telling the default value for color, for the color argument to be that species. And then the shape property, I believe it's just called shape. And we'll say that's also should be linked to the species column. All right, so let's give that a shot. And that seems to have worked. All right, we can see that the Adele and chinstrap species, they kind of occupy the same region of body mass build depth space. But the gento, those are definitely bigger birds, and they have a smaller build depth, which is curious. Maybe they probably eat different kinds of clams or whatever dependency. Okay, any questions?
So earlier you said that if you use a factor, a variable that is a factor, then you get a number of different colors, and instead, if you use a variable that is continuous, instead you get some colors that are some maybe dark blue, and then a little less dark, and then a little lighter, and so on.
Yes, that's correct. Let's see. Let's give that a shot, though. So let's see what would happen if we if instead of mapping the color of the dots to a factor or character value, what if I said this was going to be flipper? I'm going to map it to flipper length m millimeters. I hope that's right. I'm going to take out, yeah, let's see, let's run that. So here's an example where I changed it up a little bit and I said, pick a color, not from the species column, which has 3 unique values, but pick a color from the flipper length column, which is, that's a continuous numeric variable. And what it does intelligently, it says it realizes, okay, flipper length, that's a continuous numeric values. So instead of using a discrete color palette, it creates a color ramp going from light blue to dark blue. Those are the default colors. And then it uses that to color the dots, right? And you can change the color ramp with, there's a way you can change the color ramp if you don't like blue to dark blue. But yeah, so that's an example where it intelligently figures out what kind of data are in this column, and therefore how to pick visual properties that represent it. All right, so you can see this can get fun, because now we have a legend with for shape, and we have a legend for the dot color. All right, so any other questions? I like these questions and probing the envelope of what we can do here. All right, next, let's talk about facets, because what we've done so far is we're trying to use colors and shapes to show different groups of the data, right? Because this is it's 3 species of penguins and there's multiple islands. And oftentimes we have to plot groups of data in a plot. So mushing them all together on the same space with different colors or shapes, that works if it's not big data, but sometimes it doesn't work. So facets are another way that you can plot different groups of the data. And what facets do, let's just run code chunk number 9 so you can see what facets look like. So facets are where you have separate plots for different groups of data, but the X and Y range of values on the X and Y axes is the same. So you can visually compare the groups of the data and where they fall on the same axis space. All right, so it's not like we're plotting 3 different plots with different ranges on the axes. We're making 3 facets. So facets refers to a plot of one section of the data. So let's look at code chunk number 9 and talk through this. So if you look at code chunk number 9, it's the first part of it's identical to what we've been working on, right? It's just, we're just mapping the X and Y values to 2 columns. What makes this a facet plot is we tack on at the end there the facet wrap function. There's facet wrap and there's facet grid. And they both will make facets. The question is, do they make 2 by 2 or 1 by 3 or 3 by 1? So they control the layout of your facets. But facet wrap will simply what we've passed it here is the name of a column that we're asking it to use to group the data and then make a different facet plot for each, in this case, species. All right. And facet wrap just means this one has 3 groups of data. If it had 6 or 20, it would wrap those down to other rows. You wouldn't get 20 teeny tiny plots on one row. It would put them, it would somehow break up your space into multiple plots. And facet grid allows you to specify, I want 2 by 2 or 1 by 3 or 4 by 5, that kind of stuff. So it's kind of neat though, right? Because facets are an effective way to visualize and compare different groups of data. And you can take a plot and make it a facet plot just by adding one extra piece to it at the end. Now the reason, yeah, and if you might look closely that there's a tilde in front of species. We'll look at how that operates here in a second. So actually, let's do that now. So you might notice that there's a tilde in front of the species column in code chunk number 9. Basically, it's using formula syntax here, where basically, well, let me just show another example. I think this will illustrate how formula syntax. So I'm going to copy paste that same ggplot expression where we're creating a facet wrap, but now I'm going to say here, island squiggly line or tilde species, and here you can see what that's doing. It's actually creating more facets because there's 2 islands and 3 species. So the way the argument for facet wrap is read is that the first argument will define the groups that should appear on the rows, and then the second argument, or the thing after the tilde, is the column that should be used to find groups of columns, groups of data for the columns, right? So when you have 2 columns inside as the argument for facet wrap, then you're going to get a 2-dimensional grid of facets, and it's going to chop up the data by 2 of the columns, island and species. And these columns, they should be character columns or columns that have discrete values. If you had a column, if we use flipper length for one of the facet columns, that could get ugly. I don't even know what would happen if we did that. Okay, but anyway, so that's using facet wrap. Okay, any questions? All right, next, we'll do one more example. That was what we've been looking here are scatter plots. Let's look at code chunk number 10. And here we're creating box plots. So the opening function is the same, but instead of geom point, we're putting in geom box plot. And there's bar plots, you can do pie charts, you can do all kinds of stuff. A good way to get an idea of what you can do with ggplot, there's lots and lots of help resources online for ggplot. I will often Google, like, how do I make a donut plot in ggplot? I'll just go to Google and say ggplot donut plot. And within 3 or 4 clicks, I can find a sample piece of code to help me understand how to do that. You could probably ask ChatGPT. I think it could probably figure this stuff out too. But there is I think it's rgraph gallery, and this is a website which is mostly done with ggplot. But you can kind of see here, there's like dozens and dozens. Say you want to do a radar chart plot. Oh, they've got these ads going now. Anyway, so you can see some sample plots between the ads, and you click on one of these, it'll take you to the code that was used to actually build this plot. So this is a good way to visually see a plot that you might want to reproduce, and then see the code that produced it. So basically copying and adapting someone else's code instead of starting from scratch. Okay, so there's challenge number 2, which is to make a histogram of the flipper length for each species. That's too easy. It's basically code chunk number 10, but you replace flipper length. Isn't that what we have? Oh, that's a histogram. Okay. Okay, try code chunk number 11. So code chunk number 11, what we just made in code chunk number 10 are box plots for each species, box plots of the flipper length. And your job in code chunk number 11 is to make not box plots, but histograms for each of those species. And I leave it to you to think about, okay, histogram, are you going to have 3 histograms? Maybe go with facets? Or are you going to have 1 histogram and maybe use colors or something so that the different species are reflected on the histogram using colors? So they're all in the same axes, but somehow you're grouping them or coloring the values by the species. Okay, so I'll pause for 4 or 5 minutes and let you mull over challenge number 2. All right, so coming to the histogram, hopefully, yes, so we're going to start off with the same ggplot. So now the question is, what kind of geome should we use to make a histogram? And I'm going to type geome underscore and just see what pops up. And you can see there's lots of these geomes, curves, densities. I'm looking for a histogram. What's a hex? That's interesting. Divides the thing. Huh. That's some very clever people here. Okay, so if I just do geome histogram, it did not like that. Geome histogram. I'm getting a error message. Make a histogram or flipper length for each species. Okay. So I think we need to have, I'm going to take out the X. Right, because a histogram is one-dimensional, so that kind of makes sense. Okay, so there we have a histogram. Let me make that X. Okay, so what I've written so far is a histogram of all the data combined. You can definitely see there's different groups of data. So the question is like, how am I going to visualize the different species? Well, I've seen facet wrap, so that might work. So I can say facet wrap, and then put the tilde there. So that'll be three histograms side by side, and then the column species. Let's see if this works. Okay, so I have 3. So this is probably what I would do, right? Because it's easy to see them. And there's only 3 of them, so you can actually, kind of like put your head around how the distributions differ. I could also do, instead of that, another technique you could use would be, I think there's a group argument, group equals to, this is not right. Species is a group. Nope, not group. Maybe grouping. Nope. I'm gonna have to look at the answer. But there is a way that you can actually have all 3 data sets on the same histogram, but looking at I don't have any answer. Anyway, so we'll come back to that. But there is a way that you can basically have color bars in the histogram that you can see the different species. If anybody's faster than I am, feel free to throw that in the chat window. But I just want to finish up though, because we're out of time, and that was our last exercise. One thing I will take note of is that, this is really a bit of a tangent, but the geome functions also, color equals species. Thank you, Jerry. On that. That makes sense. Of course, it should be color.
Actually, fill works better. Fill equals better.
All right. This is awesome. Okay, so so histogram accepts a fill argument, which is the color, and if you tell it to use the values of a column, you get this output. right? Where it stacks them up. So that's pretty cool. Yeah, so you're really just kind of limited by your imagination. I'm going to skip over this last thing about stat function. That's really getting in the weeds. But I will say that here's an example of another geome, which is a trend line. And you create this with geom smooth. So if you do have time series data and you want to create a trend line, you can do that. And you can see the default is to create that smooth trend line, as well as the margin of error or the confidence interval of this trend line. Under the hood, it's running a regression, and there's a bunch of arguments you can use to customize that. So it's cool stuff. But it is time. I really want to thank everybody for giving up for most of you 4 Wednesdays in a row, Wednesday mornings. I had fun. I hope this was useful to you. You could probably tell this workshop series is kind of a work in progress. So I will be sending out an evaluation. I would love to hear what you thought. If the pace was too fast, too slow, you'd like to see more exercises, less exercises, more homework, less homework. If there are topics that would be good to include, like to hear that as well. This used to be a 2-part workshop series, then it became 3. Now it's 4. We haven't touched statistical modeling. We could go do a deeper dive into like certain types of data, APIs, spatial data. Ours is a big universe. So please sign up for office hours if you have any questions. I'll put the link here in the chat window to our office hours. You can probably tell I enjoy talking about this stuff. And the other folks on my team do as well. Big thanks to Ben and Genoa for helping out 4 weeks in a row. So I will stop talking at this point. I will stay on if anybody wants to chit chat about projects or anything you want to do. Otherwise, thank you again.